Hello everyone. Today we are presenting Playfair Cipher implementation and analysis. Before modern encryption techniques, classical methods were used to send secret messages. One such method is Playfair Cipher, which is more secure than simple substitution ciphers. The aim of our experiment is to demonstrate a digraph substitution technique where we encrypt pairs of letters instead of single letters. Our objective are to construct a 5x5 matrix using a keyword cryptography to perform encryption and decryption and to analyze frequency distribution of a ciphertext. This cipher increases complexity by using 676 possible letter pairs, making it harder to break compared to basic ciphers.
The Playfair cipher was invented by Charles Wheatstone in 1854 and was later promoted and popularized by Lord Playfair, which is how it got its name. It belongs to a class of ciphers called Digraph substitution ciphers, which means it encrypts pair of letters rather than individual characters. Now why does that matter? Because operating on 676 possible digraphs instead of just 26 letters, the Playfair cipher significantly obscures frequency patterns. This makes it much harder to crack compared to the simple monoalphabetic ciphers like Caesar cipher. Coming to our problem statement for this experiment. First, we have to construct 5x5 Playfair matrix from the keyword cryptography. Second, encrypt the provided plaintext using Playfair cipher rules. Third, decrypt the ciphertext to recover the original message. And fourth, analyze the digraph frequency distribution in the resulting ciphertext. Up next, let's look at the step-by-step algorithm that makes all of this possible. Now let's get into the algorithm both for encryption and decryption. Encryption rule. Step 1. Construct your 5x5 matrix from the keyword. Remove duplicate letters and merge I and J into one cell. Step 2. Divide your plain text into digraphs, which are pairs of two letters. If a pair has same letter repeated, insert an X between them. If total length is odd, then add X at end. Step 3. Same row rule. If both letters are in the same row of the matrix, shift each one position to the right, wrapping around if needed. Step 4. Same column rule. If both letters are in the same column, shift each one position down, again wrapping around. Step 5. Rectangle rule. If letters form a rectangle in a matrix, swap their columns. Each letter takes the column position of the other. Now the decryption rule. Decryption simply reverses the process using same matrix. If it's same row, shift left instead of right. If it's same column, shift up instead of down. Rectangle, same column swap. This rule is actually symmetric. It works identically for both encryption and decryption. That's a complete algorithm.
Now let's see the Playfair matrix constructed using the keyword cryptography. Here's how it works. We first write down the unique letters of the keyword in order CRYPTOGAHV, removing any duplicates as we go. Next, a very important rule. I and J share a single cell in the matrix. This is necessary because we need to fit 26 letters into only 25 positions. After placing the keyword letters, we fill in the remaining alphabet letters that haven't appeared yet. D, E, F, K, L, M, N, Q, S, U, V, W, X and Z. This matrix is the foundation of the entire cipher. Every encryption and decryption decision depends on the position of the letters in this grid. Now, let's walk through the plaintext processing and the actual encryption output. Our original plaintext is meet me at the secret location after midnight. After removing spaces and applying the digraph rules, we get 19 digraph pairs ME, ET, ME, AT, TH and so on. Something interesting to notice here is that the digraph ME appears twice and so does the AT, each of them appearing 2 times in the sequence. Now, applying the Playfair encryption rules to the each pair, we get 19 ciphertext digraphs VM, KR, VM, BY, PB. And here's a fascinating property of the Playfair cipher. Those repeated plaintext digraphs produce identical ciphertext pairs. ME encrypts to VM both times and AT encrypts to BY both times. This is an inherent characteristic of the cipher. Identical plaintext digraphs will always encrypt identically under the same key. Now, the moment of truth, decryption verification. Applying the reverse Playfair rules to our ciphertext, we get back, "Meet me at the secret location after midnight." The decrypted output exactly matches the original plaintext, confirming that the algorithm is correct and the matrix maintains its integrity throughout the process. Moving on to frequency analysis. Out of our 19 ciphertext digraphs, only 2 out of 19 repeat, those being VM and VY. This means 17 out of 19 digraphs appear just once each, giving us a near uniform distribution. This near uniform spread is exactly what makes the Playfair cipher stronger than single letter substitution ciphers. It becomes significantly harder for an attacker to spot patterns and crack the cipher using standard statistical analysis.
Now I will explain the Python implementation of the Playfair cipher. Our program is divided into 5 simple functions. The first one is generate matrix. This function creates the 5 cross 5 matrix using the keyword. It removes the duplicate letters and combines I and J. The second one is find position. This function helps us to find row and column of each letter in matrix. Third one is prepare text. This function prepare the plain text. It removes the space, splits the text into pairs and adds X when needed. Fourth one is encrypt. This function applies the Playfair rule to convert plain text into ciphertext. The fifth one is decrypt. This function does the reverse process and gives back the original message. Finally, frequency. These functions count how many times each pair appears. So overall, this function helps us perform encryption, decryption and analysis easily. Now let's see the output of the program. When we run the code using keyword cryptography and our plain text, we get the following result. The ciphertext generated is VM, KR, VM, BY, PB and so on. Next, when we apply decryption, we get back the original message, that is, meet me at the secret location after midnight. This confirms that our program is working correctly. Also from the frequency analysis, we can see that VM appears 2 times, BY appears 2 times, all the other pairs appears only once. So program runs successfully from start to end without any error. Now let's understand the analysis of our result. First one, repetition. We observe that repeated pairs like ME and AT produce the same ciphertext each time. Second one, frequency distribution. Most of the ciphertext pairs appears only once. This creates a more uniform distribution. Third one, better security. Compared to the simple ciphers, Playfair is a more secure because it uses letter pairs instead of a single letters. Finally, limitations. Even though it is stronger, it still has some weakness. For example, some pairs always give same output. It can be broken using known message pattern. So overall, Playfair cipher is better than a simple cipher but not completely secure for a modern use.
Let's summarize the results of our experiment. The 5 cross 5 Playfair matrix was generated correctly from the keyword cryptography. All 19 digraph pairs were encrypted without any errors. Decryption output exactly matched the original plaintext. Frequency analysis confirmed a new uniform digraph distribution. A Python implementation was validated completely end-to-end. In conclusion, this experiment successfully demonstrates the Playfair cipher as a historically significant digraph substitution technique. By encrypting letter pairs rather than individual characters, it achieves measurably better resistance to the frequency analysis rather than monoalphabetic ciphers. Our Python implementation confirms algorithmic correctness through round-trip encryption and decryption. While the Playfair cipher is vulnerable to modern cryptanalysis, it remains an excellent pedagogical tool for understanding classical cryptographic principles. And the key takeaway to remember is digraphic substitution increases ciphertext entropy and reduces a statistical vulnerability, a foundational concept in cryptographic design. Thank you.